I want to talk today about feature importance, which is sort of a very nice topic. And I thought it was sort of a modern topic, and we are working quite heavily on it. So maybe I should just go into it. So what is feature importance? Feature importance has several names. Some people call it attribute importance. The name interpretability has come. Explainability is also one of the terms. Basically, feature importance is to find out, once that we have a predictor or regressor, what are the features or the attributes that are important to determine the result of the predictor. That is, what is that matters? We may have a neural network that has 100,000 nodes inside it. What are it? It looks at all the data, all the bits of the data. But what is really that is affecting mostly the results at the end? What are the features that are really important? What are the ones that are not? Normally, feature importance can be done at two levels. We can do it for the entire data set, which is normally what is done. But we can also do it for a single row. Understand, in a single row of data, one instance of the data, what are the attributes, the features of this row that are making the decision. I will explain later why this is sort of very relevant in several of the applications. As you can see, I use the name features, but I'll use attributes also because I also work in the database area for quite some time. So for me, really, it's attributes, but features and attributes are interchangeable for this talk. So feature importance, we could first say, well, this feature is important and this feature is not important. We don't do that. We assign a numerical value. We assign an importance number. And the higher the importance, the more important the feature is. Later, we will assign some more meaning to this number. But let's say that this is just somehow a uniform number in some sense. It's not really based on zero or anything like that. But a difference in between two of these numbers is relevant and is the same as another difference between two other numbers when we are doing this analysis. So that we have a scale that is sort of uniform. So in a picture, what we have here is, we have some data. The data produce some predictor. And now the attribute importance is an analysis that tells me, for example, this is a banking application, that age is very important, salary is even more important, credit score is quite important, and number of children is the next one. And there are some that are, like gender and postal code and claims and so on that are not important at all. So that's the idea. And as I said, the numerical value makes sense. So if we have a difference here that is this much, then a difference that is about the same here should be about the same difference in importance from one to the other. So these values are not just random values. They reflect in some sense a scale in the attribute importance. I want to talk also about data importance. I call data importance the analysis of the data without any predictors. So when we analyze which are the attributes that are the most relevant for making a prediction, we may do this without a predictor. And this has been the subject of a significant part of statistics. So for 100 years, if you wish. And there are lots of methods and tests. We have correlations, we have linear regressions. Chi-square is extremely famous. The G test, which is very similar to chi-square, is also there. Heat maps recently are helping a lot. There are Kolmogorov tests. There are lots of things. The field is quite rich in this area. But I want to also give an example that shows that the data importance is really not completely adequate. Let me give you a very simple example that we will use more than once. Suppose that I have a system in a bank that recommends or rejects loans. And this system is very simple. It uses just salary and say if the salary is greater than 50,000, it grants the loan, or recommends the loan. If the salary is less than 50,000, it rejects the loan. Okay? So that's the system, and that's what we are doing, and it's fine. And so now we test the system from the data importance view only. That is just the data. We don't look at the predictor that is making this decision. Well, lo and behold, we'll find that it has a gender, unfortunately, it has a gender bias. Some gender is going to get more loans than another gender. So we are now seeing some effect, which is a correlation between salary and gender, but not a property of the predictor. And this is essential because in some sense, at some point you may say, this system that is assigning loans is biased towards gender, and it has to be fixed or whatever. Well, no. A good prediction, a good analysis, feature importance, based on the predictor, which is likely going to catch this dependence on the salary, will indicate that only the salary is important and not gender. So, let's start with feature importance as a goal in itself. Sometimes the outcome of feature importance is the goal in itself. We are looking at COVID-19 right now, and we are looking at what are the features, the factors at the country level that affect the number of deaths. Well, in this case, we have thousands of features. We have 3,140 features. And this is a research study, of course. We have only 150 countries to analyze. And in this case, what is really important is which is the feature that is affecting it. So we want to, the most important feature and the second most important feature and so on are important in themselves. Not for the prediction so much, but that's the data that we want to find out. Because once that we understand which are the features that affect the number of deaths, maybe the scientists can start doing something about it. Another example comes from a work that we have done for imminent fall detection in stamping presses. So in that case, it's the engineers that are interested. If we find, for example, that the vibration is a very important feature to detect a fault in advance, well, then the engineers can come and understand why this is happening. Probably it has a simple explanation, but now they know where to start looking at the problems. We were looking at a case in a smelting process where, again, the ore had different properties and different things were added to the ore. And at the end of the day, the cauldrons that do the process were having different number of months that they were lasting, with a huge cost associated with each one of those. In that case, it's also important just to know which is the factor. For example, the acidity or the fact that they were adding something to the ore that is affecting the life of the process. So in some cases, the feature importance, in particular in cases where we are talking about research problems or understanding the problem more than anything else, just the feature importance may be the goal of the process. And this is regardless of whether the correlation in the end or the dependence in the end is a positive or a negative correlation or something completely different, right? So the second use of feature importance is as a check. When we have a model and we have auditing or we have a situation where people want to understand how this has been done and whether it makes sense or not, the experts will want to understand on what the decision is being made. So it's a bit of a sanity check. The most important variables, the feature importance, determines that A, B, C, D are the most important variables. And okay, an expert may say, yes, this makes sense. And of course, it may also say it makes no sense. The phone number determines whether you're going to be sick or not. No, that's wrong. The phone number has no known effect on whether you're going to get sick or not, or whether you need to get the loan or not. Equally important sometimes is, as I hinted with the case of the loan, is checking that some features are not important. So because of regulations or because of standards or because of the internal rules of the places, you may want to make sure that some features are not determining your decision. And finally, for all the computer scientists and all the data scientists, we always learn a lot. It's not just curiosity for curiosity itself. We always learn a lot when we understand which are the features that are important in making a decision. It's part of the learning of how the data is working and how these decisions, how this process that we want to understand and predict is working. So the next part that I think it's quite relevant is feature importance as a tool for machine learning itself. We are promoting this quite intensively lately, because I think that feature importance improves the whole process of building good predictors. First of all, if we have features that are important, let's take the example of the stamping presses that I mentioned before. If we find that vibration is an important feature, then maybe we can improve the sensors. We can put better sensors. We can read the sensors more often. We can place more sensors. So if we know that something is important, this will also apply to a banking application. If we know that sort of the residence where the person lives is important for determining the loan, maybe we will want to collect more information about, is it an apartment, is it a house, how long has the person lived there, et cetera, et cetera. So once that we know that a feature is important, we may go back and work and get more information about this feature. Similarly, if we have something that is an important feature, maybe that gives an indication on which direction to get more information, more similar information to that. Maybe we catch something that is important. And at the other end, obviously, it has benefits. If we have features that are not important at all, then we should remove them. Removing them saves the time of collecting, maybe saves the money that is required to collect them, will definitely save computing time. And also, we all know that if we have a problem where we have lots of features which are not relevant, many of the algorithms will suffer quite a bit in producing good predictors, or will take at least a lot longer to produce good predictors. So the quality of the predictors is also affected if we introduce somehow random data. So it's a good idea to remove it. So a word about algorithms, because I have been sort of saying feature importance is done, and I haven't said anything about how do we do this. There are lots of algorithms these days. We are working on several new algorithms. We have permutation importance, which is a classic one. I will not be able to explain them all. That will take way too much time. But permutation importance is a very simple idea. You just get a row permuted, and if the response is much worse, then you know that that column was important, that feature was important. Shapley was a statistician that designed a test for gamblers, how to repay gamblers, and now we have found a much more useful use for his theory. And from ideas from Shapley, the mathematics of Shapley come the Shap values. We have worked on algorithms based on minimal perturbations that produce a change. We have two families of algorithms. We call them Letitia and Topkapi. Another area is sensitivity analysis. Sensitivity analysis is in some sense the equivalent of partial derivatives for numerical problems. Sensitivity analysis in some sense the same for classification problems. You basically want to find which are the attributes that produce a change in the result. We have a new algorithm called orthogonalization. For the people that are familiar with linear algebra, it's a very similar procedure to the Gram-Schmidt procedure for orthogonalization. Basically, it takes one feature at a time, finds the most important feature, takes it out, takes its contribution out, and looks at the remaining, finds the second best, takes it out, and so on. If we have algorithms for row-level importance, of course, they can always produce a complete data set algorithm, right? If we just do the row-level importance, we can do the row level for all the rows in our problem, and we have an algorithm for the entire problem. And I want to have a special word about negative controls. This is an idea that comes from science, in particular from biology. Some of you may be familiar, excuse me if I repeat that notion. Whenever you have, say, a biological experiment where you're trying to determine something, you put negative controls. A negative control is, for example, just, completely sterile water. And now you want to find whether, in the rest of your samples, you want to find whether there is a bacteria or not. Now, you run all these tests in parallel, so you really don't know which vial has the water and which vial has the bacteria. You run the whole thing simultaneously on everything. And at the end, the negative control should not show any bacteria, right? And if it shows that there was a bacteria there, then you contaminated things during the process, and so your data is not very good. Your procedure is not very good. What is the equivalent of a negative control for machine learning? Well, the equivalent of a negative control for machine learning is very easy. It's a column or a feature, an attribute, which is totally random. Now, totally random may have numerical properties that differentiate from other ones. So we typically don't do just a completely random column. We take an existing feature, an existing column, and permute it and add it to the data. So now, how does this work? At the end of the process, we get the most significant feature, the second most significant feature, the third most significant feature. The fourth most significant feature is a negative control. Well, that means that that's the end of it. Nothing else is going to be significant. Because if you reach the point where the most significant thing that you have is a feature that is randomly permuted, that has no meaning whatsoever, then nothing at that point or below is significant. And here is where the numerical values are useful, because as soon as you have a value for the negative control and you understand that the differences are sort of smooth, now you can judge, how close to my negative control is the next one most significant, and so on. And so you can get an appreciation of which are the features that are very relevant and which are the features that are really very close to being random and hence are not very significant. So it's in some sense a sanity check for feature importance, but I think a very important one. Sorry for the pun there. So let's talk a little bit about row-level importance. Row-level importance sometimes is called interpretability or explainability. And it's the ability of doing, as we have over here, for the attribute importance, but for one particular row at a time. So in the previous case, we had the individual importances, but now for this particular row, it may be that this value here and this value here are at their full, and the other ones, although for the whole problem they were important, like this 3, But now they are not the ones that call the shots. And so in other cases. So this is in some sense transforming a predictor into a diagnostic tool. Suppose, for example, that I had a good predictor that detects some form of prostate cancer. Well, it works in general, but what about when we apply it to a particular patient? Well, when it may say for a particular patient, you have no chances of having prostate cancer, or for another patient, it may have, you have. But actually what is interesting is to know what is happening, because it may be that it's your genes, in which case maybe you don't have a lot of possibilities, but it may be because your potassium is high. And so in your particular case, this example is a different one, but in your particular case, you may say, oh, for you, the problem is here. So, you are going to get the loan or get the prostate cancer mostly because of this particular feature. So maybe you can take care of it. So that is changing the predictor into a diagnostic tool in the medical case. But it can be in any application. It's sort of the same idea. Because the application for a loan, for example, is telling us why you are being denied the loan, that's where the name interpretability comes. And actually, here in Europe, we have a law that is called the GDPR compliance. In simple terms, basically, is a bank cannot tell a customer you were denied the loan because the computer said so, right? So, which is a very unpleasant way of dealing with customers, but in this particular case, now it's part of the law. You cannot use that argument. The computer denied your loan. That's it. Go away. You have to explain why. Now, managers, of course, want to explain already why a client is denied a loan. But in this particular case, the row level importance is going to allow me to tell each particular case why this particular loan has been granted or denied. And finally, I think that this is a very important aspect of it. It demystifies machine learning. It takes away this notion that the algorithm is intelligent, is doing something intelligent. No, the algorithm is just applying simple rules and is saying, in this particular case, this data is important, and that's why I'm making the decision. So again, it's in some sense trying to explain the results, but I think it has a very important factor in demystifying. A couple of caveats, I'm running out of time. Feature importance is as good as the predictors themselves. So we may have a GIGO system, right? Garbage in, garbage out. If we don't have good predictors, we are not going to have a good feature importance analysis. When we have highly correlated data, it's a problem and has to be taken care. Very flat problems where we have very few rows and many features, like the one I mentioned with the COVID, that we have only 150 countries and 3,000 features. Those again also present problems with lots of algorithms in machine learning, but in particular they present problems for feature importance. And in general, feature importance is expensive to compute. It's not one of the cheapest things to do. So if you are interested in knowing more about the way that we handle feature importance, there is a white paper. You can click on this link. I think that this presentation is going to be available for you. So I want to finish here and open for questions or
One of the questions is from Nathan. He said, is the orthogonalization algorithm similar to PCA? I heard that word once. I hope I didn't butcher the pronunciation.
No, that's fine. No, it's actually different. PCA basically finds the shape of your points in space and basically finds the first main direction and the second main direction and so on. So from that point of view, there is a similarity there. You're finding the main direction and then the second most important direction and so on. But those are for the for the data points themselves. They have nothing to do with the target that you want to predict. So in some sense, if you were using the PCA for the targets that you want to predict, actually, it's a very insightful comment, I have to say. There is a similarity there. There is obviously a good similarity, but I think it doesn't go all the way. I think it's, as I said, the PCA just looks at the data alone, whereas we are looking at a predictor and which is the most important feature for the predictor, which would be like the main direction in your case, but it's just now one feature. And then we basically take it out of the answer and then look at the rest, find the best second one, and so on.
Very good. Thank you for that response there, Gaston. What is the best feature importance for categorical data? How about numerical data? What feature importance algorithms would you suggest for very large data, say a data with above 700,000 features?
Ooh, 700,000 features. That's actually more than what we have in. I work in bioinformatics too, so that's why I am working now on COVID, and that's why I also had an example from gene expression. In gene expression, we thought that we had lots of features by having 30,000 plus features. In those cases, I think that the only answer for those cases is algorithms that have the flavor of orthogonalization, because algorithms the partial derivatives, if you have a numerical problem, will also do reasonably well in those cases, but the partial derivatives will give you all the ones that are similar, and you will not be able to extract the next. Let me explain this that actually is quite intuitive. For these problems that you have lots of features and these very flat problems where you have lots of features and very few rows, the problem is that is completely overdetermined in terms of any set of a few features will determine the results. Now, some may be correlated, and some may be correlated with the answer quite highly. Now, the problem is that because you have so many, and you don't have enough data to separate them, once that there is one that is significant, all the ones that are highly correlated with that one will all appear at the same level in a standard feature importance analysis. And so if this correlation is high, those that are highly correlated will hide all the other ones, and you'll never get to the second one most important. So when you have the problem that I didn't have the time to explain, I said, flat problems will require special analysis, is because of this, that you find the most important one, and if the most important one is correlated with many others, all these others will appear at the top, and you will never see the second ones. So there is a lot more, but to be said. But I think that's the most important problem when you have problems that have tremendous number of features.
Thank you, sir, and thank you Nafish, for the question there. Our next question comes from Deepti, I believe. I have a software developer background of 4 years. How can I pursue a career change into data science and machine learning? I am taking up an ML AI course in my master's. How do you pursue this field as it's still growing? Some career advice for
Actually, Adam, you're probably more able to.
Yeah, sure. Let's.
I can tell you only one anecdote, one sample point, which is me. I was doing databases, and we were doing relational databases, and we were doing exploratory relational databases, and then we moved into more business intelligence, and we always needed to get more intelligent answers, and that's what led us to go into machine learning. So I think that when you have a sort of an interest in data, you have to have an interest in data. If you don't have an interest in data, it's very difficult to do, in my mind at least, it's very difficult to do machine learning successfully, right? So once that you have, and as I said, I'm coming from two sides, right? I'm coming from the bioinformatics side on one side and on the database, on the relational database from the other. But, it's only one sample point. I think that Adam will have more insights about that. It's a very nice field. I really like it. I really like it. It's I was doing computer algebra before, and in the Maple system. And when you solve an equation, you get some pleasure, right? The system did something intelligent for you, and you get some kick out of it. And machine learning has the same thing. When you find, oh Jesus, it's predicting something really meaningful, that gives you a kick. I think it's very beautiful from that point of view. I am an advocate of machine learning, not necessarily artificial intelligence as a whole, right? I'm much more concentrated on machine learning.
Fair enough. Yeah, look, thanks so much for that reply. Gregory has asked, can feature importance or feature weight be determined by neural network or by a statistical approach? Is there algorithms of adjusting weight of neural network taking into account correlation of the feature importance?
I think I think that the picture was sort of a bit obvious, but we never get into the method that does the prediction itself. We always take it as a black box. So whether it's a neural network or whether it's a decision tree or whether it's a nearest neighbor problem or whatever you want, we don't look at it. There are people that look at neural networks and try to understand them. I wish them good luck. It's very difficult, and I'm not sure about how you can really make sense out of that. But we prefer the approach of looking at the predictor as a black box, and basically we poke the predictor with lots of data, and that's the way that we extract information. Also, I think that from the question, there was this statistical analysis. Please remember the part that I mentioned about data importance as opposed to feature importance, right? Data importance is a very relevant subject and very important subject in statistics. Incredible amount of work has been gone into that area because it's a very important topic, no question about it. But feature importance is slightly different. We are looking at a predictor and we are trying to understand how this predictor is working, how this predictor is making its good decisions, right? Not how the data is, how the predictor is making the decisions. So you definitely have to look at the predictors, and you definitely have to, and if it's black box, then you can analyze any, the algorithms that I mentioned there are really black box algorithms. They would work with any algorithm. Because if you look at the method itself, you become totally dependent on that particular method, right? If you analyze neural networks, then you will be doing very well for neural networks, but nothing else. You're not going to be able to handle a decision tree, right? A random forest.